with our series, and where we are aspiring to cover all the topics which you typically see in a semiconductor, going from all the way from atoms to a motherboard, right? Or different architectures. So now, here today we are going to talk about, based on what our understanding in the last lecture which we were discussing about the semiconductor. What is a semiconductor? We were discussing what is electron, what is hole, right? And so we find out that, okay, there are two different possibilities one can see of the semiconductor, or let's say three different possibilities. Um so if this is a piece of semiconductor, right, you have a possibility that this could have more holes than the electrons. So that is one possibility. That means the empty states at floor zero are more, or the valence band are more than the filled floors on the floor one, right? So that could happen in a hotel. So that is the same thing which you see in a semiconductor, and this could happen when you are doing something externally, because we saw if they are equal, both of them, right, which is equal to Ni, that means this is typically the case where you are only playing with the temperature, right? So if you have a semiconductor, you are playing with the temperature, you have N and P. Initially it was intrinsic semiconductor. Intrinsic means this had this condition, right? Whatever Ni or Pi was there, and now on top of that you are increasing temperature, and this is increasing, right? So temperature is a very important variable, and that is why we see that this exponentially depends on the temperature, this quantity of the NP. If so, temperature can really change the conductivity of these samples, which we are also going to talk about today, what is happening to the conductivity, right? So then this is the case where we say this is mostly P type semiconductor, right? And this is the case where you see N greater than P. Again, by some external influence you are doing, and it becomes N type semiconductor, right? So these are the different types which you see of the semiconductor based on how much concentration of electron. So it means how many rooms are filled and how many rooms are empty in the valence band, right? So that is the idea. Now, if we see that go forward with it, that what is happening is the semiconductor good, right? Mean for me, because in the end, okay, if it is N or P, that means that if I'm going to touch the semiconductor, is that I'm going to feel charged, because you say, let's say I am talking about N type silicon, right? N type silicon. Silicon is a semiconductor. So we know that if I'm touching this, do I feel the charge? Because it is an N type. You are telling me electrons are more than the holes, right? You should feel a charge, right? But the reality is that no, you don't. You don't feel the charge. Why is that so? And the reason for that is because even in an N type semiconductor, you say the charge neutrality, right? Neutrality would be there. So now you can say, what is charge neutrality? What are the other charges which I am not able to see? So first of all, we say looked at that when there is NP is going to be always Ni square, right? That is the law of mass action which we saw. So that means if you are doping it N type, that means you do have some holes also in your semiconductor. The only thing is that in this case, when it is N type, the N is much more than P, which you can see from here also. If N is much higher, this guy is much lesser, right? Because Ni is same, right? So that means that, okay, N and P are two different charges. What are other charges which are happening in this? And this is what we are going to talk about in another video where we talk about the doping in the semiconductor. For now, today, we are going to discuss, which is a very important topic, is called the how do this semiconductor, how can I utilize these semiconductors, right? So, okay, this is good that I have charge in the semiconductor. How do I utilize? Utilize meaning that, as you saw in the MOSFET also, I do need to apply certain potential to this semiconductor. Let's say this is an N-type silicon, right? And I apply two metal contacts, and these are my between which I'm going to apply any battery, right? Because that is what is the usefulness for an electrical engineer. If they are making any devices that you apply a voltage, you are seeing how much current you are passing. So now what happens? Let's see, if you apply a voltage to this semiconductor and you have let's say a lot of electrons which are there. So that is the case that you have chosen an n type. So a lot of electrons which are there. What is going to happen to these electrons? Would they be silent? So before, for that, first you have to see what was the picture before you applied the voltage, right? So let's say when I had a semiconductor, n-type silicon, and before I didn't apply any voltage yet, what was happening to the electrons, right? So as we saw, this semiconductor is basically like, very simply, we can represent it as a bond model where you have each silicon is tied to other four silicon, right? That is what you are seeing in this crystal, right? So somewhere in n-type, you have an external dopant, for example, like phosphorus, which we will talk about in doping again, I'm saying. It gives a one electron extra. So that means there is an electron which is there. Similar to that, there are multiple electrons like that, which will be there in this silicon. And what is happening to this silicon? What is happening to this electron? Is this that the case we are discussing at T equal to 0 Kelvin? Yes, if we were discussing a case of T equal to 0 Kelvin, this electron was not moving at all because it does not have any thermal energy. But because we are discussing when T, let's say 298 Kelvin, that means there is a room temperature. So this is the frozen part where electron is frozen, right? It's like a frozen movie. So you have electron which is frozen. If you want to freeze electron, go to 0 Kelvin, absolute 0 Kelvin. You would not see electron moving at all, right? Because it's just frozen. But because when we go to a room temperature, that is the typical condition of my devices, when I see that this is there, what is going to happen? Electron has thermal energy, right? Will have thermal energy. And whenever there is a thermal energy, what is going to happen to electron? It is going to move. It is going to move. Move means it is going to hit this, go back, hit this. So there is a path it may take for hitting these atoms coming back and like this, right? So that is what is we know as, which you have seen typically in a semiconductor, we talks about electron, that there is a Brownian motion of the electron, right, which is happening in a semiconductor or in any material, right? Because these atoms are a reality. It's not in vacuum, this electron, nicely that there are no atoms at all. It does have atom because it is in a crystal. So it is going, whenever it has energy, it is going to hit other atoms, right? So that is the reality which is going to happen in the electron. So because of that, what is going to happen? So because of that, you see that even if you don't apply any voltage, electron is moving, right? It is hitting again, then coming back, then hitting like this, right? So this is the motion kind of which is happening. So then you say, okay, very good. If the electron is anyway moving, and if I put an ammeter here, right, just to measure that when electron is moving, how much current is flowing, would I get a current out of this device? Should I get, because electron is moving, you are telling me the thermal energy is there, the electron is moving, so should I get current out of this device? And the question and the answer to that is that you would get no current, right? When no V is applied to a silicon, right? And the reason for that is because what is happening is there are, first of all, there is one electron which is having a random path, right? Like this Brownian motion. But similar to this electron, there are many other electrons because we have doped it in silicon. So that means there are many electrons like this. So these are the brothers of this electron, which are also having this random motion. So what it happens is, it so happens in statistics that whenever these random motions are having, in reality, when you don't apply any voltage, there is no net motion of electron. So that means if you see the net motion that electron has, because there is a randomness in the, so it is basically, and you sum through all the electrons, you see there is no net motion in the electrons. What it means is that if you were to see, it may look like to you, okay, yeah, internally the electron is hitting, and then there is a, because of the thermal energy, this Brownian motion is happening. But in reality, what is happening is, if you could also see it as that there is no net motion. So that means you could see it as at outside, that electron is just where it is, wherever it is, right? Because there is no net motion, there is no net displacement to this electron happening, right? So that means that is the reason why you see there is no current if you apply an emitter. So now the question comes naturally, what makes the electron go or have a net displacement or net motion, right? And that is the case which we were discussing here. So now we have seen, whenever anybody is representing these atoms without any potential, you understand that it is basically going through a Brownian motion. There is a motion which is happening in the electrons, even if there is no field or no voltage applied between the contacts. The only thing is that there is no net motion. So because of the no displacement, you could as well as think of these that they are stable at a point, right? Because if I keep moving, let's say, imagine you keep moving one step further, one step down very fast on a place, the other person may think, yeah, you are just stationary, right? At that point, yeah, you are doing whatever you are doing, dancing on a one point, but you are, for him, is stationary because you have not really reached a target or wherever you were supposed to reach. There is no net displacement in your motion. So similar to that, if the electron is like this and we apply a voltage, very good, voltage means that there is a, whenever we apply a voltage, there is an electric field which is going to come. So this is positive which we are applying, this is negative. Electric field is going to come like this. Oh wow, electric field, some new quantity which has come. What is an electric field? We all probably have studied electrostatics. We have studied that whenever there is a potential difference which you are applying, there is a electric field which is there. Very simple example of that you can imagine, like a bottle of water, right? So which you put it on a surface. If this bottle of water, right, with the cap, whatever this bottle is there, and the bottle is filled, right? It is filled. Then you see what is happening in this. There is no potential energy difference between the 2 points, right? Because that is why you see the water is kind of stable, though it may move a little bit because of whatever other deterioration, similar to our electron, that temperature was there, so it did move, right? But there was no net displacement, which is what we see also in the water. There is no net displacement, right? Because it is kept in a very perfectly same surface, right? So now what has happened, if suppose you start to pick the water or you slant it, right? So you slant the bottle, what happens? So when you slant the bottle, you see the water will start to move on the bottom. If this was not fully filled, you will start to see the bottom, there is more water, right? So that is the reason why it is happening. What do you think is happening? So first thing is, because you make this point higher in potential energy, right? So this is higher in potential energy, and this point is lower. So that means there is a net potential energy difference between these 2 points which is there. And because of that, this slanting, you see there is a force which is applied, right, to the water on this side, because there is a change in the net potential energy, and because of that there is a force which is applied. This is exactly what is happening to the electron there. When you make that, what you do is you apply a potential and negative potential. What happens to electron is, what it feels is that the potential energy at this point of electrons, potential energy of electrons, it increases at this point, right? Wherever there is a negative, and the potential energy decreases, right? So then you see that because of that, what happens is, now you would see there is a force, right? Because there is a potential energy, and that is what we are calling as there is an electric field which is coming from this voltage, and that applies a force on the electron, right? That means there is electron, now it is going to feel that I want to get to this side. And this can be also seen with a simple formula. If we see the electrostatic force, which is your QE, right? So E is from left to right, right? This is the left to right, which we are seeing. And if Q is your minus E, because your charge is negative on the electron, you see the force will go on that side, right? On the right side. So that is what is happening to your electrons, that it feels pull from left to right. And that would, now you see that there is a net motion, right? Due to this electric field, which is what we know as the drift. So drift means that there is a net motion now happening from left to right, and which is likely going to give you, so electrons will go this way, right? So that means if electrons are going this way, the current is the other way, and that is why you see the current direction is opposite to the electron. This we have studied, because current is opposite to the electron motion. So then we see that, okay, this is the how the current is going to flow in this semiconductor, right? And this is happening all the way from because of drift. And we will talk about the mathematics and everything of this drift phenomena, what is happening. That is for another video. Hopefully, we learned something today. Thank you. Keep growing, keep learning.